to the predictor head that could be acquired to do multiple tasks?
I saw some models that have first a classification on the type of question. So basically, when you the model receive the answer, there is first a classification on what is the type of this question? Is like area, is presence, is comparison, and if it's, for instance, area counting, then you do a regression. Otherwise, you do a classification.
Okay, so so then with the single backbone, it's possible to have multiple type of head, just because we can able to convert the question into a latent space, basically.
Yeah, or you just like put everything inside and like
wish best.
Yeah.
Okay, thank you.
Any other question? If not, we can thank Lucrezia for the presentation.
Thank you.
Okay, welcome back again. So this is going to be our last lecture. And it is my pleasure to welcome our speaker, Professor Mihai Datcu from German Space Center. And he will present physics-aware and explainable AI for Earth observation, image understanding, with demo of digital twin Earth system components. This is going to be the part 1. After the coffee break, you will have the part 2. Presented by him again. And I would like to introduce him before giving him the stage. Mihai Datcu received the master and the PhD degree in electronics and telecommunications from University Polytechnic of Bucharest and the habilitation in computer science from University Louis Pasteur Strasbourg. And he has held long-term research and teaching positions at the University Polytechnic of Bucharest, ETH Zurich, and especially at the German Space Center, where he led the Big Data and AI for Earth Observation Group. He also directed the DLR CNS Competence Center on Information Extraction for Earth Observation and the Immersive Visual Information Mining Lab. He is currently a full professor and director of the Research Center for Spatial Information at the University Polytechnica of Bucharest and visiting professor with ISA Philab. His research focuses on information theory, signal processing, explainable and physics-aware AI, computational imaging, and quantum machine learning for Earth observation. He has received major distinctions, including the Romanian Academy Prize, the IEEE GRSS Best Paper Award, the National Order of Merit Romania, Blasia Pascal International Chair of Excellence, and the Ed Estra Award, and the IEEE GRSS David Landgraf Award. He's an IEEE fellow. So there are so many things to say here, but I will cut it here. So I will give you the floor, Professor.
Thank you very much. Before anything else, I would like to verify if the quality of the sound is correct. If you can confirm.
Thank you.
So, thank you very much for the introduction. I'm going to present today a lecture on physics-aware and explainable artificial intelligence for Earth observation and image understanding. And I will make a demonstration with a system I'm developing at this moment in the frame of several activities. I would like, from the very beginning, to announce a surprise for all the audience, for all the students. At the end of the presentation, I will ask you to run together a mini project. So it is a surprise. I will allocate a quarter of an hour to explain at the end how to proceed with this mini project. So I'll start with an acknowledgement. I would like to acknowledge my team at the German Aerospace Center, DLR, at the Data Intelligence and Knowledge Discovery. My team at DLR and Technical University Munich Aerospace, I was leading for a couple of years. The team in Paris is a frame of International Chair of Excellence Blaise Pascal at the Conservatoire National d'Art Métier, and definitely my team at Polytechnica Bucharest as a research center for spatial information geospace tech.
Mihai, sorry, just
yes.
a second. I want to clarify to the students what you said at the beginning. The professor will do this theoretical part until a certain point. Then he will assign a small exercise, let's say, a small project. So based on what is explained, you will do this practical exercise during this first session, okay? So before the coffee break.
That will be at the end.
In the end, yes. But just to clarify, because someone didn't listen in the back.
Yes, please, if you can also pass to me the question. I would like also the presentation to be a dialogue. So every time you have question, Sylvia, if maybe you can help me to take the questions during the presentation. Thank you. Thank you very much. Okay, excuse me for interruption. I deactivated the camera during the presentation. My computer is heating. I start presenting 4 references I recommend. At the end, I will present more references. I will send you a list of references. Those which are interested to continue in this field, they could study. So these are very recent publications. They are presenting an overview and mainly perspectives. So one paper, Distributed Spaceborne Synthetic Aperture Radar. It is a paper together with the colleagues at the Beijing Institute of Technology and at Politecnico di Milano, Poligny. The paper is presenting the future of space system carrying synthetic aperture radar, which is a advanced technology and Earth observation. Another paper which I recommend from the very beginning, it is Artificial Intelligence to Advance Earth Observation. It is an article written with a team from Swiss Federal Institute of Technology in Lausanne, Swiss Federal Institute of Technology in Zurich, Technical University Berlin, Technical University Munich, German Aerospace Center, University of Valencia, European Space Agency. In this paper, the team, which we are visiting professors of the European Space Agency, PhilAb, we presented a vision for the European Space Agency, a vision on how Earth observation should go using artificial intelligence. Another new paper, which I would like to present, it is generative artificial intelligence. It's a very new concept. These are generative models which are preserving the physical meaning. And a paper presenting very particular aspects of Earth observation for artificial intelligence, physics-aware artificial intelligence. At the end, we'll come back with more references. I will start the presentation with a short movie. I show this movie as presenting the problematic we have in Earth observation today. I let the movie running, and at the end I will give short explanation.
Information being lost because data is being collected that can never be analyzed. The German satellite data archive near Munich contains vast amounts of valuable data collected over the past 30 years. The archive can store more than 50 petabytes of data on magnetic cassette tapes. It may be that these tapes hold the answers to questions that won't be posed until sometime in the future. But when that day comes, will we be able to access the data? The more data we save for later, the greater the risk of losing information forever. Even the best storage media can age and become obsolete. But maybe there's a way to master the deluge of archived images and virtual reality. Researchers are mining the satellite data archive, hoping to make its information more readily accessible. As if the archive were a library with open books lying before them, the scientists can pick out an image, dive into it as it were, and check to see whether it shows structures similar to those on other images. The computer works like an automatic sorting facility. It searches the images for components like vegetation, farmland, bridges, and water. The computer sorts the images into stacks and categorizes them by their content.
At the present, they probably store in archives more than 10 to 20 millions of satellite images acquired after the 80s. With the new era of the Sentinel satellites of the European Space Agency, the data volume per day will reach the level of 10 terabytes. This is our data rate. So we are going to reach soon thousands of petabytes of data, which is a large volume of data, and all the research community is putting huge efforts in dealing with information extraction.
Soon, we will no longer be talking about millions or billions of images, but trillions. And then it will be more important than ever to uncover meaningful information hidden in the mountains of data.
So I give a short explanation. So I presented this movie just to introduce the problematic we have in Earth observation. We have many satellites with different modalities. One is spectral, LiDAR, scatterometers, synthetic aperture radar, atmospheric sensors, gravitational sensors. All of these sensors, they measure information about Earth processes and human activities. It's a wealth of information. And actually, today, in the condition of climate change, we have a huge motivation to extract maximum information from this data, complement this observation with simulation, make predictions. And this is a big data problem and is beyond big data. It's mainly about understanding this data, extracting the information, interpreting and making predictions, and also to make scenarios for events which might happen in the future. What if? A brief introduction of the technology behind. So the movie, it is a result of a project of 4 years involving 5 PhD students, an engineer, and the goal was to design a new machine learning, which is not doing classification. It's learning the projection. So images are represented in multidimensional spaces, in spaces with thousands of dimensions. And to make them visual, we need to project them in 3 dimensions. And a projection from a 1,000 dimensional space in 3 dimensions is not unique. And the algorithms, the machine learning developed in this project was learning how to project a 1,000 dimensional space in a 3 dimension in such a way to keep in front of the operator, the PhD student in the cave, in the environment, the immersive environment, to keep in front of him all images to which he was looking. So if he was looking to an image of a football terrain, the system was reprojecting the 1,000-dimensional space in 3 dimensions, bringing in front of him the football terrains. If he was looking to a coastline or a delta, the system was bringing in front of him this information, all images. So was not a clustering, was not a supervised learning, was a supervised dimensionality reduction. So that was an example of immersive visual data mining, a solution for big data, content, semantic, and physical parameter extraction. So that was a very brief introduction. Now I go further to present some, let's say, elementary concept in Earth observation. And I start with a copy of Claude Shannon paper in 1948, a mathematical theory of communication. So in 1948, Shannon already identified that the messages have meaning. So messages, they refer to or are correlated according to some system with certain physical or conceptual entities. But at the time, because Shannon was dealing with communication like transmission of a bit stream, Shannon concluded that this semantic aspect of communication are irrelevant to the engineering problem. Situation today, so this was in 1948. Today, situation is completely different. So everything which has to do with theory of communication is about semantics. It's about physical and conceptual entities. It's about messages with meaning. So everything we are doing from internet, from search engines, search engines which are defined not on internet, but on databases, as you have seen already. Foundation models, they are about messages with meaning, physical and conceptual. And I accentuate the aspect of physical meaning. And I present a simple example. That is a Sentinel-2 ESA Copernicus satellite, multispectral. This image presents the visible band, RGB bands. And in this image, what you can see, we see the Black Sea in blue, lakes in green. We see a city, agriculture, bare land, Danube, a cloud, and the shadow of the cloud. And from the same image, it is the same image, we extract an infrared band. In the infrared band, we notice some differences. So the watercolor in between sea and lakes disappeared. The contrast on agriculture and vegetation is much higher. Why? Because infrared is sensitive to chlorophyll, and it's presenting an image of a physical parameter. Later, we notice that the cloud disappeared. How is possible that the cloud disappeared? It's a question for you. It's very simple. It's diffraction. So infrared has longer wavelength compared with visible, and it happened in this particular case as the particle in the cloud have been smaller. And the infrared diffracted, and the cloud becomes transparent. Physical process. And the shadow of the cloud is here. Why? Because infrared is measuring features closer to temperature. And in the shadow, temperature is lower. And this area in the shadow is darker. This means lower temperature. So in satellite Earth observation, we deal with a sensor producing images, but these images are not pictures like photographies. They contain physical, they sense and they carry information on physical parameters. And that is one of the main differences between computer vision and Earth observation. An example on synthetic aperture radar. All satellite images are actually not images of the scene, but that is extremely accentuated for synthetic aperture radar. So Earth observation are doppelganger. So they are not an image of the scene, they are an image of the scattering of the scene, of the signature on how the radiation is reflected. And that is a landscape, alpine, and that is a synthetic aperture radar, color image obtained from a SAR image, combining different features. And it's not easy having only this image to return to this image. So synthetic aperture radar, it's a doppelganger. It's recording the reflection of the microwaves. And from this reflection, from this signature, we need to understand all the process, direct the forward model to be able to invert and reconstruct such a landscape. Another example of synthetic aperture radar, that is a parliament house in Bucharest. That is a TerraSAR X, the German synthetic aperture radar satellite, 1 meter resolution. This image, it is a complex value image. So it has a real and an imaginary part, an amplitude and a phase. And actually extracting the Fourier transform from this image, we obtained signatures. And again, from this image to reconstruct the building and to recognize it, we need to understand the image formation, the forward model. I give another example, this time on multispectral images. So when we visualize an image, we can look only to RGB, the visual component. So our visual perception is adapted to the visual spectrum. And in here we have two sentinel images. The RGB channels, actually they have 13 channels, but we can visualize only 3 of them. And in this one, these circles, they mark 2 areas which apparently are different. In this image, these areas which are in the circles, they look visually to be similar. In reality, if we transform the information from the certain bands, we notice that actually these different areas, they are very different. They are different in 3 bands, but the other 10 bands, they are very similar. And that is not visually observable. And as this example is a contrary. We have similar visual areas, which after the compression, the transformation of the certain bands in 3 bands, they look to be different. So synthetic aperture, multispectral and synthetic aperture radar, they sense physical parameters which are beyond the visual perception. That's an example, a study in which was used a gun to learn the scattering. So because we discussed that actually the satellite images are not an image of the object. If we want to generate an image, if you want to use a gun or a generative model to like a forward model, we need to train this in such a way to reproduce the scattering phenomena, not the scene. And this is an example of a gun, which is actually representing the double bounce, the multiple reflections on of the microwave on buildings. Now, from this short introduction, we have a conclusion. In Earth observation, we deal with a sensory gap. So what is a sensory gap? The physical reality of the scene, like vegetation, buildings, scattering, and the sensed signal and the interpretation of operators. So we have some vegetation, and this vegetation could be interpreted like forest, vegetation, trees, or a park. And this is a subjective interpretation based on the same physical representation. And one of the tasks in machine learning, artificial intelligence for Earth observation is actually to make explainable. And this is an example of an algorithm which is not doing only classification, like a woody man-made structure or a smooth surface, specular, mixed woody. That's explained. It is multiple scattering. It is a volume scattering, and how much is a quantitative. It is a surface scattering. So we need algorithms which are representing the semantic, but also the scattering as a physical properties. And again, that is something very different from computer vision. In machine learning, in artificial intelligence, we need to train our models, our algorithms. Training means we have training and benchmark datasets. In computer vision today, mainly in the new development with the foundation models, we have training databases, training datasets with many millions of samples labeled. Labeling of the samples is done mainly by crowdsourcing. In Earth observation, we do not have a crowdsourcing. So looking to the image is not enough. Images, they contain this physical parameter, these signatures. And actually, in this image, we have an example of a synthetic aperture radar, a movie showing oil tanks dynamic depending on the level of oil in each of the tank. We have an elevation model. We have a polarimetric signatures in Sydney. And actually, the fact that we have huge diversity of structures, and each of the structure comes with physical parameters and signatures, we need methodologies, because this is beyond visual perception. We need tools for annotation. And we need also to have a kind of ontology, a taxonomy, trying to collect information, connect information in between semantic and physical parameters. So this is a standalone field, how to generate training and benchmark data for Earth observation. A brief outlook on application. Application of Earth observation are thousands. So Earth observation today, satellite data, the information extracted is in many, many of the products we have. Here I mentioned only three: biosphere, geolithosphere, and hydrogeosphere. So we are monitoring ecosystems like natural parks over Europe. We monitor deforestation in Brazil. Why? Because this is a contribution to the carbon cycle climate models. It's very important. We monitor subsidence. Why? Because we have changes in the elevation, millimeters of a large area, giving information about underground and also affecting structure on surface. Or we are monitoring the polar sea ice, which again is a very important factor in the carbon, as a climate change. So these are, let's say, three main applications among thousands of other applications for satellite image information. Today, after 50 years of satellite remote sensing, almost every place on the Earth was observed thousands of times. Only from Copernicus, from Sentinel, in the last 7-10 years, we have thousands and thousands of images of the same place. So today, Earth observation is not only an image. Earth observation is about time series. So movies from space. So that is Bucharest observed from 1984 until 2012, so 30 years of observation. It's a data cube. It's a hypercube because it's represented in 4 to 5 dimensions: space, time, physical bands, spectral bands. And that is a big data. Only such a data cube, it's a big data. So in such a movie, in such a data cube, we have a lot of information about urbanization. So this is Bucharest in the 80s, Bucharest in 2000. It's this area. It's about 3 times larger. We notice the construction of a highway which appears in here. We notice the airport evolution. We notice changes in agricultural practices, vegetation. We observe effect of the climate change over such a long period of time. And definitely, this kind of time series, they require very particular tools for analysis. And there is another type of information. It's beyond cartography, beyond mapping. We need to observe evolution of the processes and also to extract quantitative information from the evolution of the processes. So we need to observe evolution. Evolution with time, but also in space. So patterns are spatio-temporal patterns, things which are moving. They migrate in space over the time. And there are quantitative information we have to extract. We discuss today mainly about artificial intelligence, big models. So we have large models, large language, large vision models, large physics-aware models. But in signal processing, in information theory, we have still many resources which are little explored. And I stop only on a simple example. Compression-based pattern recognition. Pragmatically, we have a database with pictures of airplane, and we want to classify them. And how to do this? We are doing only one operation. We compress each of the image, and we write down one number, the length of the compressed file. It's just one number for all the images. Later, we concatenate an image with all the others, and we compress again. And we write down another single number, the length of the pairs of compressed data. So now we have two numbers, so length of the compressed for each of the images, and the length of the compressed file for pairs of images. And only with these two numbers, we obtain a metric, a distance, the compression-based distance, and with this we can classify. It's a simple method. It's using lossless compressor like JZIP. It is completely unsupervised, does not need any feature extraction and no clustering because it's grouping automatically the distance. This means we are completely independent from other algorithms. This means we are very much objective in the data. I only presented this to turn your attention to other methods in information theory signal processing, which they have a perspective of development. And definitely, we are in the period where deep learning, artificial intelligence, large models are applied for Earth observation. That is a typical architecture in which CNN is used to extract features. And later, there is an active learning in which an operator is indicating structure he wants to have, is confirming, and structure he doesn't want to have, the one in red. This information is sorted by a classifier, and the system is proposing a new ranking. In a few iterations in the active learning, we have a fantastic fast learning algorithm. So it's a combination of artificial intelligence with a new kind of machine learning. Machine learning, which needs only a couple of training samples, 10, 20, compared with millions for other type of classifiers. It is interactive, which means we can select the classes we want to choose, and it's also an exploratory data mining. So at this point, I present one slide from European Space Agency. So ESA decided that today there are priorities: digital twin Earth, quantum computing, and artificial intelligence. So these are actually the fields of perspective to push ahead and to enhance the use of satellite data to satisfy new applications which have been solved in the past. And the rest of the presentation, I go in some details on these topics. If there are questions up to this point. I continue. I continue with a very simple classification of Earth observation sensors. So we have satellite sensors which are very close to computer vision, to photography. These are the very high resolution optical or synthetic aperture radar. Resolution of centimeters, tens of centimeters, half a meter. In such an image, we can observe objects like airplane, airport infrastructure, vehicles, even persons. Persons mainly because they have a shadow. We can observe ships, and we can count how many containers the ship is transporting. So these are mainly carrying spatial information, patterns, object recognition or classification. We have another major category of Earth observation, sensors which are specialized to extract, to measure physical parameters. A single example, atmospheric sensor measuring ozone concentration. Another example, sensor measuring the ocean temperature. So these sensors are designed to extract a physical parameter, precise measurement of this land Earth processes. And we have other category of sensors which are measuring geometrical parameters, like the height of the terrain, surface model, digital elevation models, or very small displacement like subsidence or displacement after an earthquake. So millimeter displacement measured on area of 100 by 100 kilometers. And definitely in between, we have sensors which are capturing both spatial information, object classification, scene recognition. They contain also physical information like vegetation, water quality, and also they could extract three-dimensional information. So we have to deal with all these categories of sensors. And here I want again to stress that Earth observation has a common component with computer vision, like pattern recognition, video, object recognition, classification, segmentation. But the most important part of Earth observation is the extraction of quantitative measures like physical, biochemical parameters, and geometrical properties. I remember the previous slide. Because of these physical aspects, we have to deal with a sensory and semantic gap. Sensory gap is the difference in between visual perception and the sensor. So our perception is limited to the visual spectrum. It is a subjective perception. Sensors, they measure calibrated parameters. And the semantic gap, it is a difference in between the algorithm output, desired algorithm output, and the desired interpretation of the operator. Having this in mind, I present another example. So we have 4 images. The first image, it is a synthetic aperture radar, a TerraSAVIX image, in which, with visual interpretation, visual inspection, we detect 2 structures. So 2 bright parallel lines, other 2 bright parallel lines. If we emulate machine learning, asking the machine algorithm, the machine learning will decide they are similar. They are bright, parallel, with the same geometrical parameters. We have the same area observed by a multispectacle. So this time we understand that is a really way is Munich, close to the main station. And one of the pattern is this one, double line. It's a highway on a bridge. And the other pattern, it is contradictory to this. So this is a double bright line, a double bright line, double bright line, but a single and dark one. So optical and SAR, they could extract contradictory. Why contradictory? Because the sensor is measuring a signature, not the object. And the signature in optical and synthetic aperture radar could have a different nature. We take the OpenStreetMap, the railway, the city on the map, and the bridge with a highway. This structure is not indexed. Why? Maps are thematic, and they capture only the information regarding the thematic of the map. That is a street map. This structure is not a structure of the street, infrastructure. And we have a picture from this point in this direction. And in this picture, we notice this dark line. It is a support of the power line for the railway. And here we have two observations. We can try to fuse all this information for better understanding. If we try to fuse the problematic, the challenge, it is multi-modalities data fusion. They are very different modalities. And in the data fusion, we have to deal with contradictory information or missing incomplete information. The structure is missing from here. Or the second approach, so images, contradictory, incomplete, and the multimodal information. Or if we have only one image and we want to apply machine learning, artificial intelligence, these algorithms, they should learn not the image structure, but they should learn the physical model. So what's happening in here? So this power line support, it is this one, and this is reflecting the microwave once, a direct reflection, the first line, and is reflecting on ground and back to the antenna, the second line. So it's a doppelganger, it's a signature. And actually, the machine learning, artificial intelligence, should not learn that these are two bright parallel lines. The machine learning should learn that that is a single bounce, this is a double bounce, and these are single bounces. So we have to learn based on physical models and to learn the nature of the signature. So based on this, I go further in the part of physics aware artificial intelligence. That is a fantastic property of synthetic aperture radar. I explain in a single word. So we have a satellite. The satellite is carrying a radar antenna, is transmitting microwave, and is receiving the echoes. We obtain a synthetic aperture radar image. This is a complex value image. Each pixel has an amplitude and a phase. And we take this image and we compute the Fourier transform. Very simple, basic. And later we split the spectrum of the Fourier transform in the direction of the flight of the satellite. And we obtain two subbands and we invert the Fourier transform. And from these two subbands, we obtain two images which are physically identical with antennas which are looking to different directions. So this is a simple model based on using a Fourier transform of a complex value image. So every one of you can exercise this. You can load a SAR image from a Sentinel hub, take a Fourier transform in MATLAB and Python, take the subbands, compute the inverse Fourier, and you obtain two images, but these images are like looking to the target from different angles. If we look to an object from different angles, we obtain different information. conclusion, we have a physical model of synthetic aperture radar, a very simple one. And using this, we can extract an information which is complemented, which is enhancing recognition classification. It's a very simple example on how to embed in a deep learning, machine learning algorithm a physical property. An intermediate conclusion. So satellite Earth observation images, they cannot be interpreted like pictures. So generally, when we have a picture, an image, we make analysis of that picture. If we make the analysis of satellite images, we have to use information about the instrument. We have to use information about the orbit. When the satellite is taking images over Rome, which is a look angle, which is the time of the day. This is controlled. So the satellite operator is controlling the mission, and it knows the parameter of the instrument, orbit, and the geometry. The signals from the satellite, they are processed. We have to know how these signals have been processed and transformed in an image, in a product. All of these images, products, they are stored on some platforms. We have to understand the metadata to search to find the correct one. And when we have the product, we extract parameters like ocean color, vegetation indexes, or cloud temperature. These are physical models. So this is a process in which the image interpretation needs parameters and knowledge of the models. We need to know the parameters and the models which have been used in all this process. And this process is a spiral one. Learning how to interpret the images, we are able to understand what is missing, and we design new sensors. So that is a technological convergence in Earth observation. So Earth observation image interpretation cannot be done without the full knowledge of end-to-end mission design. So the sensor, platform, orbit, control, processing, ground generation, metadata, and the searching platform, and the physical models which are embedded. So based on this observation, we proceeded in developing a new concept for physics aware and explainable. So this concept actually is a concept in which we define the physical layers of a satellite mission. So the physical layers, they refer to the knowledge of models for the sensor and platform, like wavelength, bandwidth, polarization, incidence angle. The models of the imaging models and parameters of imaging system, like echo processing, azimuth focusing, and also the models and the parameters of terrain object, like dielectric properties, surface geometry. So this diagram is presented for a synthetic aperture radar, but this applies to any Earth observation system. So we have a model of the instrument and orbit, a model of the propagation and the image formation, and a model of scattering. And this hierarchy, these layers, physical layers, are going to be embedded in the artificial intelligence in such a way to have a complete understanding of the models. These physical layers result in a paradigm for interpretation of satellite Earth observation. So the paradigm is very simple. We have models which are known, which we could represent in a closed form. This was the example with the Fourier transform of the synthetic aperture radar complex image, which is equivalent with obtaining signals from two antennas looking with different look angles. So this is a physical model, known, very simple. We can implement it. We have models for double bounds or single bounds, models which can represent. But we have models of a urban area, scattering on many buildings with traffic, with traffic lights, with vegetation. These are high complexity things, where the model is not in a tractable, cannot be represented in a closed form. And the paradigm, it is very simple, where we have a simple model, known model, based on physics, signal processing, chemical, physical processes, biochemical. We are using this model. And models of very high complexity, we learn them from the data. And this is a role of artificial intelligence. So to complement the knowledge of existing domain knowledge with learning from data and learning models with millions of parameters. And this made the difference of the last 5, 7 years. We can do much more, obtain much more results, because with artificial intelligence, we can learn from data millions of parameters. And the paradigm, it is starting with a signal obtained, understanding the image formation. We obtain the image. In the image, we identify the signatures based on some models, mathematical, physical models we have at hand, we can manipulate. And later, from the large volume of data, we are learning the part of the model with many parameters which cannot be managed with the simple models, physical models, tractable. And this is a similar example with a bridge. In optical image, it's one line. In the synthetic aperture radar, we have 3 lines, right? Because we have multiple bouncing. Another bridge with a different orientation is the role of the orbit. So in this optical image and the SAR image, we still have the bridge, the infrastructure with 3 lines. So this is the importance of scattering and the importance of the orbit. So depending on the geometry, we can obtain objects, signatures, which are very different. Or we can have the same object with different signatures. And this disambiguation can be done using all these end-to-end models, the physical layers of the information extraction from satellite images. These are some practical examples. Optical images, there are very different objects, different type of structures, like a residential area, high buildings, or road infrastructure. These are the scattering, the signature in synthetic aperture radar, and contrary to the fact they are very different objects, their signatures looks very similar. However, if we look in the spectral signature, in the Fourier domain, their signature are very different. This property, the physical property. This means we can have tools now in the model of information to separate similarities and identify differences. So again, in optical data, there are different structures, visually detectable. In synthetic aperture radar, the signature is very similar visually, but visual is not enough. We need the objective extractions and parameter, and if we compute the spectral signature, we obtain signature which are different, that allows us to classify correctly the objects. So now taking this new paradigm as a model of Fourier decomposition of the SAR data, the models of single scattering, a single reflection, a double reflection, like a deflection on a wall ground back to the satellite, reflection on vegetation, like volume scattering, we can train deep learning architecture models, both with image and the Fourier transform, because we notice that in the Fourier spectrum, we observe signatures. So the Fourier spectrum contains some information, explicit information, physical information about the signature. The same happens in the parametric signature. And we train a network with these physical parameters. and we can implement a virtual sensor. In a network with a path pole, a polarimetric with all horizontal, vertical, and diagonal polarization, the Eiffel Tower. And we apply the model, the trained model, on a single or a dual pole, and we predict the signature. So it's a virtual sensor because we predict, we generate signature from an unobserved signal. And this is important. Yes, this is very important. Why? Because we have Sentinel-1, which is providing global and perpetual observation all around the world. Every 3-5 days, we have a new image and so a new constellation. The period of repetition will be even faster. And we have some quad-pole sensors which are not fully operational, or data is very expensive. We can train from this specialized data as a model, and later we can generate a virtual Sentinel-1 quad-pole signature. This was verified both with in the quad-pole. So we generated from a single quad-pole the quad-pole representation, and verified real, actual, and predicted data. And that was verified on a large number of structures identified on Google Earth, on which we have very important scattering phenomena. So based on these physics-aware principles, based on the fact that satellite sensors, they capture signatures of the scene, we can build these hybrid architectures, embedding known models and learning many parameters from the data. And we have a new category of algorithms, virtual sensors. So this is the architecture. In the architecture, we enter with a single complex data radar. We have a processing chain on images. We have a processing chain on the spectral signature of the data. And we add a supervised learning, a weak supervised learning, because this part is unsupervised, is learning only signatures in the data. So we add classes, and we obtain now one step further. We obtain an architecture which is learning from the signatures as a previous one. So we can separate better the classes using the spectrum of the data. But because we have the supervised learning, another example are the complex valued deep learning for synthetic aperture. So in satellite data, synthetic aperture radar and generally the microwave sensors, which are a broad category of sensors, they provide signals with complex valued. So real, imaginary, amplitude, and phase. Generally, artificial intelligence is dealing with real valued signals like images. And actually, we need to develop new architectures which are corresponding to the algebra and statistics of complex numbers. And that is an example of an end-to-end architecture, a convolutional and an autoencoder. And they have been designed for synthetic aperture radar. And they have the following properties. They are accommodating the complex numbers. They learn and they classify and predict complex valued signal, but they preserve the properties of the synthetic aperture radar. So we reconstruct, so this is the input data, and we generate in the generative model, we reconstruct the data. So that is reconstruction in the complex value. But we preserve the coherence. So So the coherence is a basic property of synthetic aperture radar. It's a physical property. And the coherence is preserved. It's preserved very well because we are somewhere in the interval 0.9 to 1. So it is a complex value architecture model, but it's much more. It's a complex value which is preserving a physical property of the synthetic aperture radar. We discussed about this subaperture, this Fourier splitting of the spectrum of the subdata, the subaperture decomposition. So we extract the subaperture from the synthesized generated data, and we preserve the coherence. So it's preserving the property of the synthetic aperture radar. So these architectures are beyond complex value numbers, because complex value numbers in synthetic aperture radar, they have behind a physical model. And this verification is demonstrating that the network, the model, was learning not only the characteristics, the classes of the signal, but was learning the model behind the image formation model and the scattering models. So the coherence is a very important property, and the subaperture is a very basic physical property of the system, signal processing property. I step in the multispectral. Multispectral, I repeat the example I presented in the very beginning. Visual inspection allows only to understand the information in RGB bands, visible spectrum. Could happen that in this we observe different areas or similar areas. However, the other 10 bands in Sentinel-2 sensor of certain bands, they contain information of very different nature. So here, this apparently visually dissimilar, they are similar. These are similar, in reality, they are different. And that's a consequence of the fact that in the infrared channels, we have a lot of physical information. One of the first example I presented was the cloud. And atmospheric effects are hindering satellite optical observation. And one objective is actually to valorize as much as possible this data. I give an example, Spain, which is assumed to be a very sunny country. The probability to have high quality optical, I mean, without hindering by atmospheric effect like fog or clouds, in Spain is 40%. So that is the chance of 40%. And that's an example in which the spectral, multispectral signature, the image formation in optical and infrared spectrum is used in an architecture, and is possible from the certain bands to extract some maximum information, so to remove the atmospheric effects. This is important. Yes, it's very important, because we can use the data for sites where apparently we do not have good observation. Of course, the image is not anymore an image in real colors. It is a pseudo color. The color represents mainly the type of land cover. But we succeeded to largely remove the effects of cloud. It's important? Yes, it's very important, because we have this low probability to have sunny, clear sky, even in Spain, which is recognized to be a sunny time, sunny place. And we have major disaster like vegetation fires, where the area is covered by smoke and ashes, volcano eruption. And for all this, we can further use, extract information from optical images, which apparently are hindered by this. And this was deep learning, which is using the spectral angular distance as a physical model for the spectral signature. Another example of how to use the physical model and to extract information. And again, this recovery of an image from a satellite image, it is obtained from a single image, is not from satellite time series, and the information is actual information. So if an object is hidden under the smoke or fog, the object could be detected. I'll go now on the satellite image time series. So these are hypercubes, at least in four dimensions, like space-time wavelength, but also physical parameter, and you can easily add the fifth dimension. I run the movie again. These are 30 years of observation. So we have a whole history of urban agriculture, vegetation, road infrastructure, airport infrastructure. We can extract information from the past, and we can reinterpret information from 80s in a different way, because we can now understand the evolution. So results which have been generated in 80s or 90s, analyzing the data as a time, they could be updated today because we have the time series. And from the time series, we can understand trends, we can understand how the evolution, we understand outliers, we understand continuity or discontinuities in the evolution. And that helps us to make prediction in the future. And also to build new scenarios like what if. And now, because this type of satellite images are actually the today products, or today Earth observation products are not anymore one image, they are time series. In this case, we need tools. And I give an example of what means a pattern recognition in time series. So if in a single image, pattern means the recognition of a water body, recognition of buildings in the city, or some urban infrastructure, in time series, the new problem, it is the recognition of a spatio-temporal pattern. So this is a transformation of a natural landscape in a working area. So this is an artificial lake. So that's 84 natural landscape, 86 working area building the structure of the artificial lake, and 2011 the artificial lake is surrounded by a residential area. So that is one object, a spatio-temporal object. And the question in machine learning, artificial intelligence, is to detect, to discover where and when happened similar processes. That is a working area in the center of Bucharest, the Parliament House. The working area is finished, and now it's a nice architectural design. The boulevards and parks surrounding. Again, it is a transformation from 84 to 2011. And the question is, where around the world happened the same type of transformation? Agriculture transformation in a residential area, it's the same transformation. And these are pieces of information extracted from satellite time series. They are never interpreted in isolation. They are correlated, for instance, with statistical information about demography. So taking information from the demographic evolution of the city, one could correlate these patterns with the population. Why? Because this residential area was modifying the statistic of demographic in this area, was modifying all the road networks, all the commercial entities surrounding, transportation, energy, communication cables. So all these are influenced by this. So this was an example on time series analysis. I suggest to make, if you agree, to make a break